Hi, you guys. Today I have with me problem 7.40 from Young and Freedman's University Physics textbook. So let's get started on this problem. Before we actually do that, please don't forget to like and subscribe if you like my videos. A 2.00 kilogram block is pushed against a spring with negligible mass and force constant K is equal to 400 newtons per meter, compressing it 0.220 meters. When the block is released, it moves along a frictionless horizontal surface and then up a frictionless incline with slope 37.0 degrees. A, what is the speed of the block as it slides along the horizontal surface after having left the spring? B, how far does the block travel up the incline before starting to slide back down? Okay, so I love energy problems, as I've mentioned a million times before. But what's great about, sorry, not what, but aside. So what's great about this problem is that there is this beautiful diagram right over, oh, I don't know why I did that. Okay. Okay. Sorry. So there is this beautiful diagram right over here. And yeah, it illustrates every single thing that we talked about in this problem. So we have this mass right over here, and it's already labeled on the diagram that it's 2.00 kilograms. The spring constant is right here, and we know that we compressed it 0.220 meters. So it went from here all the way to here. Great. Plus, we also know the incline that's also labeled. Okay, so what is the speed of the block as it slides along the horizontal surface after having left the spring? So what is happening is that the spring pretty much compresses it so that this is the new box, right? So this entire box in the dotted line. So the dotted line is where the box is going to be placed after it's compressed to 0.220 meters. So it's moved from this position right over here to this position right over here. Okay. So when we compress it all the way, what happens, right? So once we compress, that means that we it's the energy that's stored is elastic potential energy, right? So once we compress, we have elastic potential energy. Okay, so that's what happens. Okay, then this question is asking, what is the speed of the block as it slides along the horizontal surface after having left the spring? So once we're done compressing, so done compressing plus let go, what happens is that all of the energy that was stored as elastic potential energy turns into kinetic energy, right? Provided that there's no friction, right? So that turns into kinetic energy. So that's what's happening in this problem. Okay, so also let's take a look at B. It says, how far does the block travel up the incline before it starts to go back down? Okay, well, we know that when an object changes vertical position, that becomes a change in the gravitational potential energy, right? And if we start with some amount of, we go from here to here, and then we go back to here, right? So that's going to be 3. And then while we still have all this kinetic energy, then it goes up, right? So it goes up and turns into gravitational potential energy. So it goes from kinetic energy to gravitational potential energy. And at some point, all the energy that is kinetic energy turns into gravitational potential energy, right? So if we have an object that has like some speed, right over here, this ball, as it rolls up a hill, right? Logically, we know that it's going to roll up with that kinetic energy that it has. It's going to reach some point, right? And then it's not going to go higher than that because it doesn't have enough energy to go higher than that, right? In fact, the opposite will happen is like, the opposite will happen where it rolls back down. So like similar situation right here, right? Where we have some sort of box and it has all this kinetic energy that was converted from the elastic potential energy all into kinetic energy, and then all the kinetic energy is converted into gravitational potential energy. Right? And just like an aside, right? An aside would be, sorry, the aside that I wanted to tell you is that, yeah, like at some point, at some maximum height, it can't go higher than this, right? But at some point, like right over here, it's going to have both kinetic energy plus gravitational potential energy, right? It's going to have both of those. Similarly with when it's compressed somewhere here, right? So when it's still partially compressed, plus it's also moving, it'll have kinetic energy plus elastic potential energy, right? It'll have both those things. And that's a little bit of energy. But okay, let's get back to the problem. I know we broke down this problem before we actually wrote down all of our knowns. Sorry, I'm a little bit out of it. Obviously, I haven't done a video in a really long time. I've been in Europe and Asia, and I'm also like moving to a different state soon. So I just have a ton on my plate. But thank you for watching and liking my videos. I really appreciate that. And I also really appreciate those of you who've reached out to me on like social media. As you might already know, I have like an Instagram where I sometimes post, but kind of infrequently. Okay. Knowns. So knowns are mass, right? It's 2.00 kilograms. The constant, the K constant, which is 400 newtons per meter. The compression, X, is 0.220 meters. Okay. The slope, right? So let's say theta is equal to 37.0 degrees. Awesome. Okay. So let's go back to A. What are we looking for? So we are looking for what is the speed of the block as it slides along the horizontal surface after having left the spring. So again, remember how we said that at point 2, right? All we have is kinetic energy. I mean, sorry, elastic potential energy, right? All we have is elastic potential energy. Okay. Then what we want is the speed once it leaves the spring. So all of the energy from the spring turns into kinetic energy, right? That is at stage 3, right? So 3, that's kinetic energy. So we know that the energy, because there's no friction in the system, the energy, 2 and 3 are equal to each other, right? So we know that K, half of kx squared, which is the elastic potential energy, is equal to half of mv squared. And what we're solving for is the speed. So what do we have to do? Well, that means that we have to isolate for V. And how do we do that? Well, first we can cancel out this half and this half, right? Because we have half on both sides, so we can cancel that out. And because we're isolating for V, we can divide both sides by m, right? V squared. And then we can square root both sides. So then we have V plus minus V is equal to kx squared over m and then square root of that. Now, all we have to do is plug in our values, right? And once we plug in our values, we have V is equal to, and I have this in my notes, but I'm also going to double check because for those of you who have been watching for a while, you know that sometimes when I didn't double check my work in the earlier days, I would mess up sometimes. It would always be really small, just like typos on my, like misreading handwriting and stuff. So I just really make an effort to redo the question a few different ways and a few different times, and then also recheck all my calculations on a calculator just to make sure that I'm minimizing the number of mistakes that I make. Okay, great. So while I was plugging that in, I got 3.11 meters per second, and that is exactly the speed that I got when I did the problem on my own, 3.11 meters per second. Okay, perfect. So we have our for A, we have our V, which is equal to our speed, which is 3.11 meters per second. And I don't even know why I'm writing in like an absolute sign when it's asking for speed, right? So not direction. We just have to give a magnitude, just 3.11 meters per second. Perfect. Okay. So now let's look at part B. I'm going to go ahead and erase this so that we can do part B right over here as well. Okay, so part B says, how far does the block travel up the incline before starting to slide back down? Okay, so as we said, at like stage 3, right, it's all kinetic energy. And the maximum height can be determined when all the kinetic energy turns into gravitational potential energy, right? So pretty much we have like when 3 is equal to 4, and that means when half of mv squared is equal to mgh. So we can cancel out the m's on both sides, right? And we want to know how far the block goes up the inclined plane. So because we're looking at this distance, right, we're looking how far up does it go? And what we have is h. We need to find a way to relate d and h together, right? So we know that d sine 37 is equal to h, right? And we can pretty much just replace this value right over here. So we have half of v squared is equal to g times d sine 37. And now we just need to isolate for this distance d, right? Okay, so we have our 3.11 meters per second here, and we're just going to plug in all of our values. So we have half of 3.11 squared is equal to 9.8, and then we don't know what d is, and then sine 37. Again, you could have probably isolated for d first, but I didn't, but we can do that now. So I'm going to isolate for d, and that is d is equal to half 3 My handwriting is so messy. 3.11 squared, okay, divided by 9.8 sine 37. Okay, so I'm going to plug this in to my calculator again, just to make sure that I did all my math correct earlier. And yes, so the answer that I'm getting is 0, D is equal to 0.82 meters. All right, so that's my solution. And that is the answer to A and B, right? So B, D is equal to 0.82 meters. I hope that was helpful. As per usual, if you have any questions, please don't forget to leave them in the comments, or you can always send me an email as well. Sorry, I've been really bad at replying to comments lately, just because, again, I mentioned like I've been in Europe and Asia, and yeah, just busy with some other things. But thank you for watching. Please don't forget to like and subscribe. I'll get back to your comments as soon as possible, and see you next time. Bye.